Okay, so question 6. A ball is dropped from a window and takes 1.6 seconds to reach the ground. So first we need to identify what kind of motion is that. So it's a ball that is dropped and it's moving vertically down. So it's acceleration. All right, the ball is accelerating with starting velocity to be 0 as it's dropped down. It's not thrown, it's just dropped. So we need to find the height, right? So height, that means it's the displacement. So one of the Subat equations is displacement equals starting velocity times time plus half acceleration t squared. So as the ball was dropped, that means starting velocity is 0. Therefore, this term over here will be 0, and we only have displacement to be half a t squared. Now, since we're talking about vertical motion like a free throw, acceleration is equals to g, which is equal to 9.81 meters per second squared. Therefore, this a can be replaced with g. So we substitute the numbers, half times 9.81 times 1.6 squared. So if you do the calculations, you'll get an answer of 12.56. When you round it, it will be 13 meters. Therefore, it's B. Then question 7 and 8, they are about springs and extensions. So we can see that there's an increasing force applied across the end of the wire, not a spring, a wire. And then the corresponding extensions are recorded. A force extension graph was plotted for the wire. So you can see the graph over there. So question 7, the point marked X is the elastic limit of the wire. So this is the elastic limit. Just a reminder of what the elastic limit is the point where the wire in that case stops behaving elastically. And what is the elastic behavior is that when you remove the force, the wire should return back to the original length. And also remember that before reaching the elastic limit, there is one more which is called the limit of proportionality. So limit of proportionality. What is the limit of proportionality? So what is the limit of proportionality? It's the region where the force and the extension are proportional. Alright, so they are a straight line. That means the wire obeys the Hooke's law during that part, and then when it reaches the limit of proportionality, after that it doesn't obey the Hooke's law. The increase of the extension along with the force, they are not proportional anymore. So from this graph we need to find out which one is not correct. Sometimes it can be tricky. Alright, so which one is not correct? So let's see. So Fe is the maximum force at which the wire behaves elastically. Yes. So after that, if you increase that force, you no longer have elasticity. So the first one, it is correct. Then B, the force is the maximum force at which the wire obeys the Hooke's law. This one is wrong. So this will have been correct if we're talking about the limit of proportionality. All right, so since we're talking about the limit of elasticity, that means we have passed the limit of proportionality. So therefore the maximum force to obey the Hooke's law was where the limit of proportionality is. And so we found our answer, and we can just see the other two that they're correct. The force is the minimum force at which the wire permanently deforms. This only happens after the limit of elasticity. So yep, that's correct. And then F is the minimum force at which the wire behaves plastically. So the last two, they pretty much mean the same thing. Then when it comes to question 8, it says that the force on the wire was then decreased and the corresponding extensions recorded. The values were plotted onto the same axis. Which of the following is the correct graph? So now, from the graph, you can see that we have passed the limit of elasticity. That means for these values of forces and extension, we have plastic deformation. And as I've said before, what is plastic deformation? It means that when you remove the force, it's not returning to the original length. So the graphs here, they're talking about extension. That means if it's returning to the original length, we were expecting the line to reach back to the origin. But since we don't have elasticity, we have plastic deformation. That means it's not going to return to the original length. So definitely these two are out because we can see that is returning back to the original length. The first one means that the way I increase it, it would just stay there. Even if I remove the force, it's not going to go back, but it will go back. So in this case, the right answer is C. All right. You can see that the extension is getting less as we remove the force, but is not reaching the original length. So this would be the final deformation. So questions 9 and 10, they are about viscosity. So viscosity, again, remember, is the resistance to flow, right? And we have the student that carries out a practical to determine the viscosity of a liquid. A small metal sphere of radius r is dropped into a cylinder of the liquid. So we're putting elastic bands across the cylinder, and then the time taken for the sphere to fall between two of the elastic bands is going to be recorded. So this is one of the core practicals of A-levels. The question is asking us to choose which of the following are the best two elastic bands to use to measure the time taken for the sphere to fall. Now, the answer on these would be 3 and 4, this and that. And the reason is because once we drop the sphere, at the first part, it would be accelerating. So, and why it would be accelerating? Because if we look at the forces that are acting on the sphere, we have the weight, we have the upthrust, and we have the drag force. So at the beginning, the weight is greater than the upthrust and the drag force, but as it moves down, the drag force increases, and at some point it will reach a point where the weight will be equal to these two, and this is where the sphere reaches a terminal velocity. So once the sphere reaches a terminal velocity, it will move at a constant speed, and this is where we want to measure the time while it's moving on a constant speed. So that means we have to allow the first part of the cylinder, we're going to allow the metal sphere to reach terminal velocity, and then we're going to record from 3 to 4. So why terminal velocity? Because if you look at the Stokes law equation, the velocity that is part of this equation is the terminal velocity. And this is something similar that is asking us on question 10. So the sphere is made from a metal of density R and a liquid of density R liquid. So which of the following expressions correctly gives the forces acting on the sphere when traveling at a terminal velocity v through the liquid? So as I said before, if we have the cylinder here, so when the sphere reaches terminal velocity, that means the weight is equal to the upthrust and the drag force. Now we're going to break down this into different parts. Now the drag force, it can be calculated by Stokes law. So instead of D, we can say F, just to match with the equation. So the Stokes law, it's a formula that we use when we're dealing with viscosity, the one I have written above. This is what it is. So you can identify that equation there. Then we have to find the upthrust. Now, upthrust, we know that is equal to the weight of the displaced liquid. That's Archimedes' principle. So if we find the weight of the displaced liquid, we can find the upthrust. And we know that weight is equal to the mass of the liquid times g. Now, how can we find the mass of the liquid? We're going to use the formula for density, which is mass over V. So for the liquid, I'm going to rearrange that. So mass of the liquid will be equal to the density of the liquid, which is given here, and also that will be multiplied by the volume of the displaced liquid. The volume of the displaced liquid will be the volume of the sphere. So we know that the mathematical formula to calculate the volume of the sphere is 4 over 3 pi, then the radius, which is also taken as a known fact. It says that there. So that would be cube, radius cube. So therefore the equation for the upthrust, if I substitute mass with that value over there, then I get 4 over 3 pi r cube times density for the liquid times g. So I'm substituting m. This is my m, as I can see from here. Now something similar I'm doing for the weight. So now we're going to find the weight. This is the weight of the actual sphere. So like before, mass of the metal times g. So we're doing something similar as we did with the metal, with the liquid. So it will be the mass of the metal to be equal to the density of the metal times the volume, right? And the volume again is the volume of the sphere. So in that case, we have this relation. So if I replace that, it will give me, again, I'm replacing this m with that m now. So that will be 4 over 3 pi r cube times the density of the metal times g. So we have three expressions now. This for the drag force, this for the upthrust, and this for the weight. And as we said earlier, in order for the sphere to move in a constant speed, that means the forces have to be balanced. Therefore, we're looking at weight to be equal to the upthrust plus the drag force, right? Or if I move everything into the same side, it will be F plus U minus weight. This should be equal to 0. So where do I see that? I see that in option D. So this is F is added to upthrust, and then the weight is subtracted.